In this video, we want to take a look at Euler equations, in particular ones where the corresponding quadratic equation has complex roots. So here's your standard Euler equation and the corresponding quadratic equation. So what we're assuming now is that this has two complex roots, and we know that with real coefficients, the complex roots will come in complex conjugate pairs. So a plus bi and a minus bi. So in this process, of course, we got this quadratic equation because we assumed that our solution was going to look like y equals x to the r. So the question is, if r is equal to a plus bi, what the heck does x to the a plus bi mean? What is it equal to? Well, let's do a little algebra. Using properties of exponents, I know that x to a sum of two things is the product of x to each of the individual pieces. So this is x to the a times x to the bi. Now, we did work earlier this quarter with e to the imaginary power. What about x to the imaginary power? Something other than e. Well, I'm going to figure that out by converting it into e, because I already know how to do e. So this x to the bi I'm replacing with e to the natural log of x to the bi. And then I can use the property of log and pull the exponent out in front as a multiplier. And then I have e raised to an imaginary power, because essentially I have b natural log x times I. And I know what e to an imaginary power is. By Euler's formula, this would be cosine b log x plus I sine b log x. Of course, that was all multiplied by x to the a out in front here. So x to the a plus bi is x to the a times cosine b natural log x plus I sine of b natural log x. Likewise, we could do the same thing with x to the a minus bi, and essentially just replace all the b's with minus b's, but the cosine's an even function, so the cosine of negative something is the same as the cosine of the positive something, so the minus sign just goes away. Sine, on the other hand, is an odd function, so the sine of minus something is minus the sine of something, and the minus sign pops out in front here. Okay. So now the general solution to that differential equation should look like this: C1 times one solution plus C2 times the other solution. Now we're just going to do some algebra and move some stuff around here. So first thing I notice is I can factor out the x to the a, so that's up in front. That's all I did on that step, just factor that out. Now I'm going to distribute, I'm doing two things on the next step. So I'm going to distribute the C1 and the C2 into both of those, and then I'm going to gather like terms. I'm going to say what's the coefficient for cosine, what's the coefficient for sine. So for cosines, I see a C1 cosine and a C2 cosine, so that's C1 plus C2 cosine b log natural log x. And then for the sines, I see a C1 I sine and a C2, actually minus C2 I sine. So there's the C1I minus C2I times, there's an extra I in there. Let's get rid of that. Yeah, that looks better. And then I notice that what I have here is just a constant times cosine and a constant times sine. So I'm replacing the C1 plus C2 by a capital C1, and I'm replacing this stuff by a capital C2. And my general solution looks like a to the x times C1 cos b natural log x plus C2 sine b natural log x. So essentially the two independent solutions are a to the x times this cosine b natural log x and a to the x times the sine of b natural log x. Now let's do an example, see that in action. So here I've got x squared y double prime plus 4xy prime plus 4y equals 0. I'm assuming, I didn't write this down, I'm not even taking my own advice here, I should be writing, I'm assuming that y equals x to the r, so I know what to do with the r once I find it, right? R squared, 4 minus 1r, and plus 4. So this is r squared plus 3r plus 4. Using the quadratic formula, I got x equals -3 plus or minus the square root of 3 squared minus 4 times 1 all over 2 times 1. So the real part is -3/2, and the imaginary part is 7, radical 7 over 2 times I. And my solutions look like x to the -3/2, c1 cosine radical 7 over 2 natural log x plus c2 sine radical 7 over 2 natural log x. Did I mention at the beginning that, again, I am assuming that the x's are positive here, so I'm not worrying about the absolute value on those logs. I will deal with the negatives in the next video. Now I want to take a little time here to look at the graphs of these types of solutions, because some really weird things go on. So what I've done here, I have the graph of, what did I do? I said that C1 was equal to 0 and C2 was equal to 1, and had WAMAP plot the graph. Now this really does not show what's going on here. So I want to take a closer look at this and zoom in here. Okay, so this is now looking kind of at the backside of WAMAP, where I am creating the graphs. And what I want to do is I want to get a better look at what's going on here. One of the things that's happening is not visible because so much is going on in this region close to x equals 0 that it's not being picked up by the plotter here. And so what I want to do is, rather than doing the radical 7 over 2, I'm going to do 10 times that. Essentially, I'm going to increase the frequency of the ups and downs here. Okay. So I'm going to call this a 13.2 rather than a 1.323, and replace the graph here. And this gives me a little better idea as to what's going on. All I've done is made it go up and down more rapidly than it was doing otherwise. But what you can see here is that this is going up and down really, really many times. In fact, I could try to zoom in and see. So rather than plotting from 0 to 10, let's just plot from 0 to 1. And yeah, what's happening here is it looks like each time it's getting, the period is getting less, the frequency is getting higher. And then this just starts plotting things off its range and it stops plotting. One thing I could do is I could make this so that, well, the amplitude here is being defined by the x to the -3/2 power, right, next to the -1.5. That's this function here, and then of course minus that on the other side, the amplitude function. If I just made that, let's say, I got to do it up here. If I made that just an x to the 0 power, which would just be 1, then the amplitude would be the same on every one of the bumps. And what I can see is that as I move in towards 0, the period is getting less and less, or as I move away from 0, the period is getting more and more. The thing is, the sine curve, if it's just sine x, right, the input x is just increases, starts at -infinity and increases in a very steady way up to infinity. And the sine goes through infinitely many cycles. Well, I don't have the sine of x, I have the sine of log x. And log x has the property that between 0 and 1, the output of log runs from -infinity to 0. So the sine of log x has to run through all of the cycles it would run through as its input runs from -infinity to 0. And that's infinitely many of them. So between 0 and 1 here, this is going through infinitely many ups and downs of a sine curve, more and more and more as you get closer and closer to that, to x equals 0. And likewise, on the outside of 1, this graph would keep going up and down, but the periods would be getting longer and longer because the log curve doesn't, y equals x just goes up. The log curve goes up quickly to start with, but then still keeps going up, but it does it very slowly. So these sine curves keep getting longer and longer in length. They don't get taller, they just get longer and longer in length because the log is slowing down, right? But as you head towards zero, the log is approaching that vertical asymptote, so it's starting to go down really rapidly, and you start going up and down infinitely often on this up against x equals 0. So remember, x equals 0 was a singular point for this differential equation. And so we would expect maybe some asymptote or something like that. But the results here can be really crazy, depending on what the number here is and what the exponent is there. So for instance, we started off with an exponent of negative 1.5, and that was creating I mean, it's kind of an asymptote at 0, right? The function keeps getting really big, then it gets really big negative, and then really big positive, and really big negative. It just keeps going back. It zigzags up and down infinitely many times. With an x equals 0 here, we saw just amplitude staying the same all the time. If I had like a half here, then it actually is, because the square root function is coming down to 0, and this is closing off. It looks, maybe it'll look a little better if I were to zoom back out to 10 here. So there's a square root function that's describing the amplitude. And so this, although there's infinitely many ups and downs there, there's not really an asymptote at 0, because the bounding function here, the amplitude function, heads to 0. But with a negative exponent, you would have it heading up to infinity as you approached x equals 0. One of the things that I really like on this is if I go back to the amplitude being just 0 here, so the amplitude being, sorry, x to the 0, so the amplitude is always 1. Here it is from 0 to 10, right? I'll zoom in from 0 to 1. Actually, let's go from 0 to 0.1 or 0.01. It's really hard to tell what scale you're on because it looks pretty much the same. That is, I can see 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe I can see 10 bumps here before it starts getting too crazy. But when I zoom in a little closer, I can see what, 1, 2, 3, 4. I'm pointing with my finger at the screen. You can't see that. 1, 2, 3, 4, 5, 6, 7, 8. You know, it's about the same number that I can see before it goes crazy. Or I could do, let's say, 0 to 100 or 1,000. I'm 0 to 1,000, and it's still 1, 2, 3, 4, 5, 6, 7, 8. I can see that many bumps. But on the, it's hard to tell what scale you're on because it looks the same almost at any scale. You can definitely see the scale when the amplitude function isn't just 1, right? That is, if this is anything other than a 0 here, there will be either some increase or some decrease in the amplitude as you head towards 0, right? I said 0.01. It still didn't make much difference. Let's try 0.1. Right? So yeah, this is headed down with that positive exponent, and it should be headed up if I make that exponent negative. Made it smaller, but this should be getting big in through here. Can't tell that it's getting big yet, but if I zoom in, a little more, yeah, see, that's definitely less than 1 there, getting bigger than 1. Zoom in a little more. Yeah, you can see that it's starting to grow. So the shape of the graph of these solutions has these wiggling sine curves that go up and down infinitely often. At the singular point of 0, you might have an asymptote if this exponent is negative, or it might not have an asymptote and everything converges down to 0 there. It could be even continuous at 0 if you define it to be 0 at 0. Then there's no problem when you have a positive exponent here. Okay. Anyway, there's complex solutions. They're kind of fun.